Again, my name is Christian Sasse. I'm the astronomer in charge for iTelescope. I love the cosmos out there. I'm sure just like you too. And this July, we were blessed with a beautiful view of a surprise visitor from outer space. And that was Comet Neowise, which is named after the NASA spacecraft that discovered it at the end of March this year. And on July 23rd, you may remember, it went through the news again. It came as close as it could to Earth, which is still over 100 million kilometers away, or 60, 70 million miles. It's a long distance. That's about the distance to the sun. So what a remarkable event this has been, because Comet Neowise, and we have so many comets. Comets are very common, by the way. There are about 1 trillion comets out there. We don't see them, but they're somewhere in outer space beyond Neptune, all the way to the Oort cloud. But those of the ones that come, occasionally they come incredibly close to the sun, and they give us a marvelous joy. Now, we with the telescopes can capture a lot more than the Neowises of this world. But Neowise was absolutely spectacular because we could really visually see it, and I'm quite sure a lot of you went out and actually photographed it just like me. And you see that in the background, by the way. This was in beautiful British Columbia. We usually have a lot of clouds, but you can see the comet was incredibly visible. That was a time lapse that I did that you see in the background. I spent many nights out, and I was also watching a lot of you. I didn't want to take any time on iTelescope, but I was watching a lot of you look and try and do some imaging, which wasn't always very easy. I know that, and that's exactly what we're going to address today. But just to talk a little bit more about the comet, what you will have noticed, and even in the background as it runs, that a comet has two tails, right? There's a bright yellow tail, which arises from the reflection of the sunlight onto the comet dust trail. And it also has a blue tail, which we call the ion tail, and that is from the ionized carbon monoxide in the comet. So the yellow tail usually is curved, and the blue tail usually points, well, it's away from the sun, but it points in line to the direction of the sun, which makes it quite amazing. So what is the coma of a comet? The coma of a comet is the core, the outer core, that then diffuses. So thanks for the question here. So that's the outer, so that's the core of the comet, and it's surrounded by gas because as the comet gets closer to the sun, it's more or less like a dirty snowball that's quite fluffy, and whatever gases are trapped in there, like carbon monoxide and so on, slowly get gassed out through, and they're also ionized through what we call the solar wind. That's a charged particle wind impeding onto the comet, which is heating it up at a drastic rate, especially when the comet gets very close to what we call the perihelion. That's the closest distance to the sun, and that usually causes, or very often causes, a comet to split up into parts, which makes it really difficult to predict. And that gets to another important point. Comets in general are not easy to predict. It takes astronomers months to properly predict their orbit. Okay, great program. What are the good exposures time? Yes. Now, Fairlin, you are, of course, jumping ahead of time. We're going to get there, okay? So let me give you an outline now of how I would like to proceed. I'm first going to give a very quick introduction. It's only going to take 5 minutes, how we take some images with iTelescope. And then I'm going to give you the differences between comets, or what we call near-Earth objects, to what we call the stationary objects and targets in the sky. Nothing is really stationary. Everything moves out there. But relative to us, the movement is so small that we don't notice it. Astronomers do notice it, but we don't notice it for our images. So it's more like static. By the way, those of you who are German, I grew up with the word Fixstern, which is a very appropriate term, which means Fixstern is a very good way, and I never understood that when I grew up, but it means that the stars are basically fixed onto the sky, which is the way we really see it, because we don't really perceive the motion of the sky. But it's very different with comets, because comets actually, because of their crazy path and orbit, and I will go into that a little bit, around the sun, actually do show quite a motion, and that can be quite a lot, and we'll see how that affects our exposure and also what the best possible exposure times are. Hi, Mario from Spain. I see that. Very nice to have you all. Okay, so let's go. I'm going to start sharing my screen now, but that's just a quick comment. So anyway, when you first come to iTelescope, you press on Start Planning here. You come to what we call the planner. We're trying to make this as easy as possible for you. So I'm just going to change my background image very quickly so it doesn't get too annoying with the movement. So let's jump onto New Mexico skies for those of you who are in North America and also in Europe, just in the evening. So we are, of course, here still during the first half of the morning. I'm, by the way, based in Vancouver, out of British Columbia in Canada. So let's click there and you just press search and you get a lot of beautiful targets here that you can choose from. And I'm just going to choose one target very quickly because all you have to remember for iTelescope is the name of the object. And then you have the link and you don't have to remember any of these coordinates. So let's just do that. I'm going to click here and we come to a website which we're working very closely together. It's called Telescope. It's very nice. And this is, by the way, called the Iris Nebula. It would be a good target here in New Mexico skies. And this is quite an important graph. Every single object has its rise. That's when it rises above the horizon. In this case, we define the rise time as 30 degrees, as like the 30-degree line, right? So, oh, I see a lot of questions coming in, and I will address them. I will address them in a moment. Okay, thank you very much. Just keep on your questions, and once I'm through this, I'll pause, and then we'll go on from there. So every object has its rise and its set time. We have put what we call a 30-degree line here. You see that green line? It's a 30-degree line above the horizon, so it's not the true horizon. It's the line where the atmospheric distortions and also the observatories, most of the observatories should be able to see from 30 degrees upwards. So that's our virtual horizon that we defined. You can put it lower if you want to, but you can see that in this case, we can observe the object. That is night time. That's daytime here. That's nighttime. So you can see there it gets dark and you can see somewhere from 9 p.m. the whole night you could image this. So it's perfectly symmetrical at the moment, right? So usually every object, and I'm just saying this right now already because this is going to play an important role, has what we call a right ascension and declination. Those are the coordinates of the object in the sky, right? Those are our, or what we call our equatorial coordinates, and they're sort of fixed in the sky with the object, right? As I said, the movement is very small of these. So that is the definition. So usually you don't have to know these coordinates because you can just use the window here for iTelescope, and it's very nicely done. We press an iTelescope, and you could choose from different telescopes. Now, we chose New Mexico skies here. And by the way, this is a free website. You can link there. So you can see this is for New Mexico skies already, as it was linked with an API into this website. So we could choose different telescopes. So for example, if I choose T24, and you can see it's a 24-inch telescope, it's got that's the focal length and so on and so on. The most important really is the field of view. It says half a degree. How much is half a degree? It's about the diameter of a moon. That's half a degree. So that's not bad. That's quite a large view. And there's another thing we're going to get into that's quite important. It's the position angle of the telescope. I'll go into that in a moment. Let's click on it for a moment. And you can, let me just get rid of this. And you can see it would be beautifully framed here. So in this case, that would be a good telescope. We have wider telescopes and so on. But that's in general how you would define it. And you can see there's the field of view of the telescope is always fixed in the sky. The orientation is fixed, right? And that's quite important. I'll get to that in a moment because we'll need it for the comet. Because you want to know how to frame your comet. That's where I'm going to, okay? So that's just the quick introduction. And then I'll show that in a moment. You can enter those coordinates, or you just, in most cases, you just remember the name. It's called Iris Nebula, and you remember the name of the telescope, and off you go, right? So that's the easy part. So let me just stop there because now we're going to jump into comets. And before I go to comets, I'm going to read your comments and just quickly respond to them. Okay, so give me a moment here. So the Coma I have responded to is the dust where the comet was before. Yes, exactly. So the comet, typically these comets have a diameter about 1,000 miles or more, right? Very difficult to estimate, by the way, very difficult because it's usually very bright. And by the time they see the comet, it's usually quite close to Earth because they're usually very dark. So yes, the dust tail is what the comet is losing. You know, actually many years ago, in the times of the dinosaurs, these comets must have been incredible because, of course, they were a lot bigger. Those that would come regular to us, like the Halley Comet, must have been absolutely glorious. You know, they very bright and so on. So they're, of course, losing in brightness every time they go around the sun. They heat it up and they lose some on the way. So the comet is actually, you know, it's like leaving a, you know, a crumb, you know, what you call this a crumb trail, right? That's what a comet is really doing. So yes, that's right. Is it possible to do spectroscopy for an iron-tailed Mr. Scientist here, Andreas? Or, no is the answer. We cannot with our instruments. Is it possible in general? Absolutely. But we cannot at this moment do that. We are building a new observatory. The only reason we are a little bit behind with the observatory is the COVID-19 to get planning permission. But we're going to build a second observatory, and we do intend to make spectroscopy part of this one, dedicate one. But that's something that will be the later part of next year until all this COVID thing has settled. Can you tell the magnitude at its highest point? Yes, we can. That's a great question. I will get to that in a moment because I will show you you know, what the website are. By the way, the magnitude is very difficult. It's very confusing about comets. The magnitude you will find there is a huge spread in what they call the magnitude. It varies sometimes all the way from 4 to 5, all the way to 8 or 9. So the astronomical scale, anything between 1 and 5 is bright enough that you could see it without city light, right? 1 being the brightest and 5 being the faintest. And our eyes, by the way, perceive things logarithmically. It's not linear, right? So if the brightness increases, our eyes see it logarithmically. That's also how the scale of astronomy came in, because from scale 1 to scale 2 is a logarithmic scale. It's actually 2.5. It's probably 2.5 times dimmer. So it's strange. So 1 is brighter than 5. You would think it's the other way, but it's not. So the sun is somewhere around -26, if I remember correctly. So it's incredibly bright, right? Comets are also usually quite bright. There have been comets in the past that have been so bright that you could see them during the daylight. I myself have never seen that, but I've seen some very bright comets. Okay, so the answer is yes, you can. Will you talk about planets? No, I will not be talking about planets. Unless I will not be talking about planets. That's a separate issue. And I can answer that, not a separate issue, but in a separate interest area. We do not have the abilities at the moment to properly image comets with iTelescope. Why? You think, well, that's so easy from my backyard. Why can't you do it, right? I do it from my backyard. And the answer is quite simple, because telescopes for planets have a very long focal length. That means they have a very large zoom, right? We're zooming in quite a lot. And by doing that, it's actually a very small field of view, and it's very difficult to find guide stars then. Guide stars, we need to guide it. We need to give the precise location. Now, everything can be done. And fortunately, software in the astronomy world is evolving at an incredible rate. So the pattern recognition of skies and stars is improving a lot. So again, this can be done, but it's going to take some work. And yes, we do plan it in our new observatory to install it. So at the moment, I don't advise you, please. I mean, Jupiter and Saturn are going to look quite disappointing. I'll be very honest with you. So that's, I know it's disappointing, but that's the truth. Okay, Israel, can you said the comet ionizes when they come near the sun. Is that how the telescopes were able to observe the comets and their way? No, okay, I'm just talking about the physics here. The ionization of carbon monoxide comes because of the ultraviolet light from the sun, right? That's the ultraviolet light exciting it. So that's what gives it light, right? So it then goes into the visible spectrum too, making it very bright for us, right? That's why we can observe. And of course, you can observe comets in many ways, but I'm talking about the optical spectrum here, right? The optical spectrum, that's what we're doing here. We're looking only at the optical. You can use radio waves, you can use X-rays and many other things, but this is beyond the scope of iTelescope, okay? Please also plan to verify, yes. Rupesh, I completely agree with you. So this is a great request. Someone who wants to, I love optics. My background is optics. From a PhD, and I completely hear where you're coming from. I completely hear where you come from. We do plan a static wide field and a very wide field array. That's not going to be a telescope, but I completely agree with you. Yes. So one more question, and then we'll get back to it again, and then you can ask more questions. General question from Edward Roberts. For a newbie considering observation project, is it possible to use any of the telescopes to measure light curves from close binary stars in nearby open clusters or variable stars nearby? Comets may be a good, okay. So Edward, you are a scientist. So the answer is yes. We have what we call photometric equipment on some of our telescopes. Those are, especially T17 is a very scientific. So you can take the proper light curves. We have some members who take incredible precision of exoplanets, right, and so on. So the answer is yes, you can. Of binary stars, yes, you can, and open clusters too. Depending, of course, on the resolution of what you're talking about, and also the magnitude. So yes, it can be done. And if you're interested in that, there is a scientific community. There's also the large VFOT, the AVSO community, and a lot of these data are directly linked to the server. So the answer is yes, it can be done, and it is very often done, especially by university. We have many universities participating, very like Harvard and Stanford and many others. And NASA, by the way, also has a program with us. So they do these type of measurements, right? So the answer is yes. Okay, let's jump back again. I'm glad I'm getting all your questions, so don't hesitate to continue. So let's get back now and jump onto comets. So the question is now, where are the comets, Christian? This is very nice, but that's not what I came for. So if you press here on targets, you will see there's here a possibility. And again, the Telescopius site is completely free. Register with it and explore it. And there's also a small tutorial, by the way, on iTelescope. So if you press on here, you will see that it comes to comets and asteroids, but I actually only want the comets at the moment. So here you can see the option here is you can, by default, I think it's comets and asteroids. I say comets only. So we look on the right, and the first thing you say, well, that's nice, but where is Comet Neowise? Well, it's not there because you can see the default here of the horizon I was talking about. That's the artificial horizon, is defined as 30 degrees above the horizon. So let's lower it a little bit. Let's go to 20 degrees, and suddenly Neowise appears there, right? So what is it that we're seeing here on the right-hand side? And there are many different other websites, but I really like Telescopius because I'm a very visual person and they just visualize it beautifully. So you can see here, by the way, the bright, you'll see that a lot of the most bright comets that are visible and very detectable by our telescopes have a certain pattern. You can see they're early in the evening visible. So that means they're in the western side of the horizon, right? And then you see a few odd ones here too. Some here also coming up in the east, as you can see in the morning, and so on. And those are a bit further away where you can see them the whole night and so on. That's how to interpret it. But these close ones are going on similar paths as Neowise, and you can see they're visible in the early evening. So you can see now we have the coordinates there in right ascension and declination, okay? And these are the coordinates you usually need. So at the moment, it would probably be okay just to copy them and putting them into a plan. I'll show you that in a moment how to do that. But there's a problem because actually the comet is moving, and this isn't very helpful. We're not getting anywhere really here. So is there a better way of doing this? And the answer is yes, and I'm going to show you that as an example with an app now. And I also wanted to say, the Comet Neowise has been incredibly good for all of us because it has really motivated software producers such as Astropixel Processor, that's Mabula Haverkamp, who I know very well, and I work together with him to also inspire him to improve the feedback that I get from you or things that I see myself. So he's working very much on a Comet registration, and that'll be another part of a further series that I'm going to be broadcasting. That is the image processing. So that's to come in a few weeks as soon as his beta version is stable. It's already working now, and it's very promising, but that has encouraged a lot. And the same is with Sebastian, who I also know well. He is the developer here behind Telescopios, and he's doing an absolutely marvelous job. I'll show you his projection of the future that he shared with me last night of, you were talking about the comet, how to properly frame it. So all that is upcoming. It's new stuff that is really inspiring the whole world to improve their processes, including iTelescope, which I'll also talk about. Okay, so in short, this doesn't really help us very much. So what I wanted to show you, there's a toolbox here that's quite useful. And there's a telescope simulator, right? Telescope simulator allows you to go anywhere in the sky. So I can press here target selection, and you can actually put the coordinates in, and you will see the behavior of objects exactly in that coordinate. Now, it would be nice if I could just put neowise in there, but it wouldn't help me very much at the moment. I will show you in a moment what Sebastian, the developer of Telescopios, is up to. He's got a marvelous vision. Because, I mean, we're here for, you want to know how to frame the comet, you want to know how to frame the comet tail. Well, it turns out to be that with iTelescope, there are 3 different ways of actually programming or booking the telescopes to do a comet, and we're going to go into that. I'm going to show you some user images too, how exactly they have done this and what the advantages and disadvantages of each method here is. Let's jump a little bit. So I have several links here that I'm going to share with you. By the way, all these links, you don't need to copy them now. You will find on the invitation that you got, I put all these links in, but I'm going to share them anyway with you now. So let's just, if I can just find the share button here. Let me see. Those are the questions and answers. Now, where do I? Yeah, that's a little bit daunting at the moment, because because I've been sharing. One second, I'm just going to unshare. I'm going to unshare in order to find the screen again. Yes, I need to find the screen here. So I can find the attendees, and I can somehow, how do I share my chat now again? Okay, let's just go here to everyone, all attendees and everyone. I found it now, okay. So this is the link, that's the first link. So I'm just going to keep this open, and now I'm going to share my screen again. And hopefully this time it will stay that way. So let me just do that again, share screen, and get right back to this share. Okay. Yeah, unfortunately that window has disappeared again. It's a bit odd. Okay, anyway, so this is quite useful. This is where all our observatories are located. Why do you need this? Because in the apps, they often ask you for the location of the observatory. So that's the link that I've just put in. That's just that you know where they are, right? And then we have another one. I've just completed this. This has been a long request. It's the overview of all telescopes. I'm definitely going to share this one with you. So I need to stop sharing the screen again in order to find your participant. Can I find your chat without doing this? Let me see. No, I can't. At least I don't know how. So I'm going to stop sharing and get this right back again and share the link here. There we go. And then we jump back again. So this is quite useful for you. In this is all the information that you need on the normal level. Of course, you'll always have more questions about the telescopes. And as you can see, I've divided it here by observatory. So if you click on this link, I won't do this now, you will get, by clicking on that link, you will get all the technical information. But the most important you really need to know is the field of view, right? That's how big it is. Once again, half a degree is the moon, approximately. Whether it's a color telescope or not, this is a color one. the type of telescope. And now comes something that's really important. It's called the position angle. Now, what on earth is that? So the position angle, I'm just going to take my iPhone here to demonstrate this to you. So if I hold my iPhone up, the usual way you hold the camera would be horizontal, right? That's in landscape mode, and that's the way we define our telescopes to do exactly the same way. It's a landscape, the horizontal view. That's 0 degrees. And usually we have north pointing up. That's just the way it's mounted. You don't have to remember that. But whatever happens, it always has a fixed view to the sky, right? So the orientation never ever changes with respect to the direction north. That's important to remember because some cameras actually are like this, and some cameras are a bit skew in Spain. You may have noticed that, but anyway, it's almost impossible to get them always at 0 because the cameras are maintained and so on. So there may be some shifts, and that's also what is lacking at the moment is the adjustment of the horizon, right? So anyway, so what does so that would be 0 degrees. If you turn clockwise, you're turning east of north. East of north is clockwise. That's just the way we define it. So I'm turning, this is now 90 degree. You see that? It's 90 degree. That's for T14 and T20 typical. Those are Comet, very good Comet telescopes, refractors in New Mexico sky. And that's the way the camera's orientated. Now, there's only really the horizontal and the vertical position. Everything else is symmetrical. So if this is 0, that's 90 degrees. If this is 180 degrees, it's 0 degrees anyway. And for those of you who know telescopes, that's the meridian flip. It doesn't play a role. And the same with going 360 degrees. That's the same as 0. So there are really two or some intermediate positions that you have to remember. And that's important for later when I show you the app. That's why the position angle is important. There's another thing that's important, and that we had a lot of discussions and input, and that's where we definitely need to improve at iTelescope, and we're doing that at a very rapid pace. That is the minimum elevation in degrees, right? So that's a virtual horizon that we define around the observatory, where if the telescope goes underneath that, it'll give you an error message back and say, hey, the target is below the horizon. Now, that can be really irritating for the comet hunters because that's not the truth. The truth is that the horizon very much differs, and it very much depends where the telescope is located in the observatory. I mean, for example, for those comet hunters looking out in the early evening, you're looking west. You're looking north, northwest. That's your direction, right? Now, if the telescope's on the east wall, and we have that inciting spring oil in the middle, they can certainly look lower. So the horizon would be defined at the moment as looking on the west wall, which is a very conservative way, and it certainly is dissatisfactory for those who are interested in comets. So we're changing this now. We're going through all the telescopes, and we should have this finished in 1 to 2 weeks, where we have the correct horizon in there to give you the abilities to look at comets more. Okay, so anyway, that's what we are doing to put in the correct horizon, and we're really scanning the wall very carefully at the moment. It takes a lot of time, and we have to find slots also at night where you're not on. So we definitely don't do that during comet time. We do that, and we can't do it when the observatory is closed either, because we need the elect horizon. We really have to scan that very carefully. So it takes quite some time to do it from telescope to telescope, but that's what we're doing at the moment. So in about 2 to 3 weeks, this should be a completed project. So that's important at the moment. Then there's the Observatory Code in there too. Now, the Observatory Code is just an international observatory code that you need, and I'm going to show you why you need it when you want to know the exact coordinates, okay? But everything you need is in this table, together with what I've shown you there, together with the right ascension, together with the longitude and latitude, the latitude and longitude here of the coordinates that you need for apps, right? Okay, so that's quite important. So these two links are hopefully useful. Now let's jump into comets. This is where it really gets exciting. I wanted to just share some Comet websites with you, and I'm going to copy this again, just stop my screen sharing. Maybe by next time I can figure out how to do this in a better way. So let me just go back to the chat here. Okay, and share it here. So this is the COBS website. And it has all about comets. This is really for specialists, right? So everything in here that you can possibly find out, no surprise here, recent observations, you will see the designation.
I'm having trouble hearing you.
Okay, that's my Apple Watch. My Apple Watch always has to interfere. Yeah, I have a problem hearing you too. I don't want to hear you right now. Okay, so this here is the COPS website, and you can see a lot of information here on observations. So if you want to see any news, it's quite interesting. Let's just click on the news for a second. Okay, so you can see here, for example, a new comet was discovered called Amaral. I actually talked to Leonardo's his name just a few days ago. It's quite remarkable. He's got a small observatory in Brazil, completely self-financed, and he's an absolute researcher. Quite incredible. So he's got an automatic comet survey, and he discovered this comet at a magnitude of 18. That's crazy, right? That's quite crazy. Competing with these big satellite institutions like or surveys like NEOWISE, and he managed to do that. That's quite important. So you can see everything that is important there, right? And observations and so on, statistics. You find that on the website. I won't go into this, but it's quite important because there's also information here about the comet tail, actually. Again, not important at the moment. I just wanted to give you a quick overview before we go into the nitty-gritty of the image itself, of what the orbit of comets actually looks like. And very good for this is the Sky Live. I'm just going to copy that too for you. 1 second, stop sharing. Okay, let's just see how to do this again. Here's all the messages. Okay, there we go. And I'll share my screen again. So this is beautifully done. This is really beautifully done. As you can see, I have already put Comet NEOWISE in here. And here it is. Yes, there. So I put it at a date where it's just, I'm just going to do set time. You can see here that the time is set on the 4th of March. Now, why is this beautiful? For those of you who don't know, most of our planetary system is actually on a plane. It's almost like a plate, right? So everything is rotated. That's Kepler's big model, the way he modeled it very cleverly, centuries ago. As you can see, all our planets are here are more like what we call the ecliptic. That's a plane, right? And NEOWISE is coming in. Now, the question always is, what angle is that actually coming in at? And you can rotate this around, and I'm just going to try and start the simulation here, animate. So here comes the comet. And you can see its path there. Can you see the path here? It's in slight gray. You see how incredibly steep to our ecliptic this is coming in. It's coming close to the sun, which happened on the 3rd of July. Watch this now. By the way, the tail orientation is not correct here. It's unfortunately static. They have not modeled the tail. But I just wanted to show you the steep path that it's coming in. They really don't care about our ecliptic. They come in at any angle. And here you can see we're going to October and so on. And if you think about that, the comet was only discovered at the end of March. You can see how close in our solar system it was at the time it was discovered, which is quite remarkable. So you can see there how steep the angle is. That's the inclination. The inclination, I think, here is over 120 degrees to the ecliptic, right? So that's important to know because when you look at a comet's tail, it's three-dimensional. It's three-dimensional. We are only seeing a two-dimensional picture because the comet is coming in at such a skew angle. Sometimes the tail could be facing towards us, away from us, and the iron tail could do similar crazy things. And that's because of the orientation of the comet relative to the ecliptic. And we're sitting there on Earth, and we're only seeing part of the whole thing. We're not seeing the three-dimensional. We're seeing a two-dimensional picture of this, right? So that's the explanation for that. Quite useful anyway. So let's jump back here now to, let's jump right into a system. So I've jumped now onto T14. T14 is a good, is a very good example for taking comets in New Mexico skies. It's a refractor. And again, I'm referring you to the table, to the overview to really see which field of view is suitable, okay? But at the moment, as I said, Telescopius doesn't yet have a beautiful interface where you can see all that. That's why I'm skipping that, but it's going to be implemented. Okay, let me just see how your questions are doing. Okay, oh, I got a lot more questions. So let's just jump into here 1 second. Anurag, yes, Anurag, can addition of swan band filter reveal additional detail? Well, we don't have that type of filter. We don't. So the answer is I've heard of that filter. So I think I have to think now, if you're talking about a processing filter, and I think you are, there is, but I'm not sure whether you're talking about an optical filter. I'm not quite sure. There are two types of filters you can have here. The one is an optical filter, which in this case, we don't have the band filter, but we also, there are very special filters that you use for, well, looking at the frequency response of the details of the comet. There are special filters that you can use to really take out the beautiful details of a comet. So that of course is a very advanced option. So I can't really go into that. Ferlin says, I'm trying to figure out which scope to use for good framing. Yes, we are going to get to that right now. Rupesh, can you please repeat the telescope's name having portrait field of view? Well, just, Rupesh, that's easy. Just go on to the overview here. So the portrait view, if it's 180 degrees, it's the same as 0 degrees, right? So that is a landscape, right? I'm rotating it by 180 degrees. So this is landscape. This is landscape. The third one is landscape. Here you got T14 has portrait view. That's portrait, 90 degree. 90 or 270 is portrait view, right? I'm turning it like this, 90 degrees or another 90 degree to that. Yes, 270. So those are portrait views. That's a portrait view and so on, okay? So that's just imagine it's 0 degrees is horizontal and then just start turning 90 degrees. 90 degrees where we then, what was it? 270 degrees, of course, and then 360 degrees, right? So that's how it goes. So 0 degrees and 180 are landscape, and 90 degrees and 270 are portrait, okay? And that's how the orientation works. And then we have some that are in between, right? So 159 is definitely almost 0, which again corresponds to landscape, okay? And they are portrait and so on. Maybe I can add a column just to make that clear, you know? So it's a good point. I will maybe add one here just to say that's portrait mode or landscape, right? But that's the way it's defined. Thanks for that question. Next one. Wilfried, yes, Wilfried, you wrote to me earlier. Greetings from München, very nice. So telescope 40 and telescope 20 would be a good choice concerning large full. Yes, they would. They are very popular because, I mean, look at Neowise. It was enormous. I mean, when I saw the first pictures pop up of Neowise on the, on iTelescope, I was blown away. I couldn't believe it because honestly, in my time, I hadn't even realized it would look so gigantic. So people ask me, well, how can you do a mosaic? And I'll get into that. So there are a lot of questions there, but yes, the answer is and actually the framing is very important, Wilfried. So yes, we'll get into it. John, a very advanced user. Thank you for addressing the minimal elevation issue. I knew you would say that because you're one of those guys who are saying, why don't we do it? It was a major nuisance. I bet it was. I bet. Yes. I can only agree with you. Look, I'm very much on the user side. That's also a good thing because I push things in iTelescope from a user perspective. I completely get it, John. I can only offer our apologies that we didn't do it earlier. We are working on it. I completely agree. Good point. Okay, so let's get right back now to creating a plan. I said earlier there are 3 different ways of doing this, right? So let's do the first way. So the first way would be, you see where it says Comet and NEO, right? Comet and NEO. That's near-Earth imaging. So it's very easy. So the way it's done, that's that's the first way. And I'll show you what that results in. And this works, okay? I'm just going to call this NEO-wise. You can call this plan plan, you can call it Robert, you can call it your cat's or dog's name, your wife's name, whatever, husband's name, it doesn't matter, right? Any name you like. So I'm just going to call this, and because we are using what we call the ephemeris here, that is an approximation of the orbit that is going to compute, right? And from there, deduce the real-time central position, that's important, the central position of the comet, right? So it's going to appear, the head or the core of the comet is going to appear in the middle of the picture, right? So I'm going to call this, just because it's called the minor planet code, I'm just going to call this MPC1, because that's what the code is. Now comes the target name. So the best way, if you don't know the target name, go back to Telescopius, go back here, and look for your comets and asteroids. And on comets only, this is Neowise. There are many comets named Neowise, so this can give you the wrong name. But the name to remember is this one, C/2020 F3 in capital letters. I'm just going to copy this in capital letters. Very important. It has to. Unfortunately, it's quite important to do it correctly. Maybe in our case, I don't remember. It's also in small letters, but. How should I say, the scientific community comes from the Fortran age, right? The Fortran, for those of you who know programming languages, Fortran is very strict on definitions, right? And if the structure is not completely correct, it throws you out. And so that's where it's coming from. The scientific community is very accurate in these things, so that be careful with the designation. So the correct comet designation is C/2020 F3, right? And that's where we get it from. So always use that. You can type in Neowise, you'll be lucky, but be careful, you could have the wrong Neowise there, right? Okay, so I'm going to just paste that in here, and then I'm going to say get ephemeris. Okay, so what does ephemeris mean? That is part of the orbit. That is a precision orbit. And I'm going to go into that in a moment, what this strange code is about, but I won't spend too much time on it. So it says here it produced a line, and it got this off a database. And this here is this will, in real time, as soon as your plan will start, and that's part of the reservation system, of course, once you've reserved you've reserved your session, it will exactly at the time when the telescope starts, look up the real-time right ascension and declination. So it'll take into the true position and put it, and should place it, if the telescope and everything technically works correctly, should place the head or the core right in the middle of the image, right? That's what it will do. And this is what it does. And then it says local horizon above 30 degrees. And you can see that's nonsense, really. That's nonsense, because you're not going to image this at 30 degrees, because Neowise is hardly ever over 30 degrees. So ignore the start time and end time, because you have a 5-minute window here. Much better. And we may have to improve this later to specialize it for comets. So maybe with Telescopius, that this goes lower to 20 or 25 degrees, or even, which would be better, to make it real with a horizon that actually exists in real time, and really per telescope, right? So that's not implemented right now. So ignore the imaging start time and end time, but it tells, this is important, that this is correct. And that's all you need. Now you'll say, well, that's strange. Let's go into here. Look, see all those empty spaces. Oh, that's crazy. I don't need these empty spaces. I'm going to erase them. Don't touch this. This is Fortran code. And if you erase any of this, there'll be an error. So my advice is, do not touch this at all. Keep your fingers away. Now, one thing is important about the ephemeris. How long is it valid? Usually, if you want to be accurate, I would, if you make a plan in future, let's say you make a reservation in a week's time, right? And you use these ephemeris coordinates, probably it'll work. But I have had situations where the ephemeris wasn't correct anymore. So I would diligent, and you can overwrite your plan later. You can save this plan, and just a few hours before you run your plan, so in the future, you just overwrite it. I know I'm jumping a little bit ahead, but I'm looking at the specialists here who are saying, well, how do we do this? Well, it's easy. You just overwrite your plan. You just ask for the ephemeris again and save it there. Now, the most important question then is, okay, this is fine. What is the exposure time? And that's a very interesting question. So let's think for a moment what's happening here. The telescope in this case is moving along with the sky, right? It's called sidereal tracking. Sidereal means it's moving with the stars or with the sky at the same time, right? So that's what's happening. The comet has its own real time, and that's the second way you can program it. And I'll show you some images in a moment to that. So the sidereal, this is doing sidereal tracking. So usually it depends on how much the comet is moving relative to the frame. How do we estimate that? I'll show you that in a moment, okay? But very good standard parameters are 60, 120, or 180 seconds. That's very good. I wouldn't go over. Neowise is very bright. It's very bright. You don't need more. So stack if you can, right? So, and luminance is also the key thing here, right? Why is luminance the key? It's not the color. You can easily just take one red, green, blue, or if you're lucky, you can take two red, green, blue, very short. But take the luminance that gives you the contrast and the sharpness. Spend quite a few. So I'm just going to put 3 there because comet time is usually quite limited. And I'm going to put here something like 120 seconds in, okay? 60 seconds also work quite longer, only in a special mode. I'll get into that in a moment, but that's usually quite good. 60 seconds, if you really worry about hitting the observatory wall, go for 60 seconds, right? And then in this case, I'm just going to put in 1 red, 1 green, and 1 blue. And I'm going to put it at the moment at 60 seconds and bin 2. So I can't get into a lot of detail with binning now, but binning is putting the because that's more for the beginner session. But binning is putting the pixels of the camera into a super pixel, which takes in this case a 2x2 array, so it's much more sensitive. Okay, it's going to be a lot more sensitive, and it makes it 4 times as sensitive, but you lose resolution. For colors, it doesn't matter. You're getting the contrast from the luminance. So I'm just going to give you a typical one to start off with. Like this, and put this on binning 2, and I'm going to do the same because red, green, and blue compose the colors, right? So we take red, green, and blue. Some telescopes have the designation R, V, and B, just that you know. Putting in 60 seconds again, and binning 2. So this plan, how long will it take? So we've got 1 times 200, so we've got 120, 240, that's about 300 seconds, right? So this is going to execute fairly quickly. Right, fairly quickly, and this would go. So you can see the minimum elevation here is 25 degrees, and we'll try and get it a bit lower, if possible here. Okay, don't worry about the maximum exposure. So that will already, if you were to image tonight, that would work, right? So there are some options here, and there's one option that's very interesting, and it's only that's the second way of imaging. You have another option here: track on. Track on says start orbital tracking of comets and asteroids. Requires ephemeris. Of course, they have to know the accurate coordinates in real time. And it's recommended. I disagree with that, by the way, to recommend this. I don't recommend it. And I think, we're probably going to remove this recommendation. I'll tell you why. So at first, this looks like something fantastic, right? So what we're doing now is we're tracking the comet in real time, but we're going to leave star trails. So if you want details of the comet, that would be a good idea. However, there's one thing: you're losing the beautiful background of the stars. In most cases, if you take short exposures of 60 or 120 seconds, the relative movement, because a comet is fairly diffuse except for sometimes the very detailed, very sharp ion tail, it is enough with 60 or 120 seconds, even because it's the relative movement of the comet to the sidereal tracking is small, that it doesn't really matter. So in general, I do not recommend that, but that's what track on is there for, right? So it tracks the time, it'll leave star trails. I'll show you what these images look like. Let me just jump to this very quickly. So this is I picked out some user images. I'm going to show you how this beautiful image here was done. This was done on T14. And this was done with only right ascension and declination coordinates. That's the third method I'm going to show you and how to do that. So there you are able to place the comet exactly where you wish you can do. This was done. Here is a good example Oh, let me first show you the other one before we get to this. Sorry. Let me first show you this. This here, you can see the comet head is right in the center. So this was done with, I put here a designation MPC. So that was done with the ephemeris. So this would be a result that you get. And this was a, gosh, what was the, let me just check for a second. I don't remember. Yeah, this was a 300 seconds, quite long. So 300 seconds results a little bit in a diffuse, this was a luminance bin 1. You can see here a 300 seconds image that was taken with T20. And you can see it gets a little bit diffuse here, but still beautiful, you know, very beautiful. So you do lose something here, right? Because through the ephemeris, the core is put in the middle, right? And you, well, it depends. Now here you have some beautiful background galaxies, right? I mean, depends on the composition really that you're looking for, right? So unintentionally, serendipitously, this is actually a beautiful image. Now I lost, hang on, no, here we are. Then let's see what track on looks like. Here's orbital tracking on. You can see exactly what's happening here. So this is getting beautiful details of the comet here. You can see some very nice details of the comet, but you're losing the stars, right? You're losing the stars because it's tracking the comet now. So this can be nice if you've got lots of time, right? If you've got lots of time, you may want to do the comet there and then stars and superimpose them if you're an advanced Photoshop user. But in general, I don't recommend this because as I said, my next session will be on using software like AstroPixel Processor to show how we can really beautifully image the comet without losing too much detail and keeping beautiful stars in the background. Okay, so that's quite important. How does it look on T68? Well, that's a typical image here on T68, also quite beautiful. Again, here the minor planet coordinate, so the MPC1 line was used. Our apologies, some have asked with track on, we had some difficulties with T68, so I have to apologize. We fixed that now, right? But that's how it would look. Again, the head in the center, so that's a one-shot color camera, right? Something else here. Yeah, that's another bin 1. I think that is, let me just double click on here to see. This was a 120, yeah, this was a 1/22 image. So you can see this here, beautiful. So 60 to 120 seconds seems to be a very good way. If you really don't have time, and the comet is very close to the horizon and you have a small window, then go for, let's go right back to the, here. I then suggest you go for luminance 1, 60 seconds, bin 2. I've seen some people do it, and that you lose the resolution for the comet, but you get a lot of signal to noise ratio, right? Because you get a lot of faint details. So that's also a setting that works very well in that case, okay? So anyway, I've said it now. So what we do now is that was the track on thing. I've explained now how that looks. So I'm not going to enable track on. I'm just going to say create a plan for later, which I'm doing now. And that's it. There's our plan saved. And then we just attach it to a reservation. I'm not going to do that now because that's too much. That's more something for the beginner scope that I'll show next week. For those of you who want to know how to do it, just go to the to iTelescope and look at the webinars for new members. I have got some recordings there of how to do all that. Okay, so that's important. Just very quickly, let's take a moment and look at this ugly code here. And what do these numbers actually mean? Well, there's an explanation, by the way, here. But I'll quickly tell you what. The first space is reserved here. This is reserved. Then comes the comet name. Then here, that's 2020. Here you see 2020-07-3. That is the moment when it was closest to the sun, right? So that's a perihelion when it was closest to the sun. So that's on the 7th of. You can see the 3rd of July. That's in decimal coordinates exactly to the second when it was closest. And then come a few other ones. This here is the eccentricity of the comet. Then you have here, that I definitely know, that's the inclination angle. And that is another angle because you have two angles. It's a three-dimensional problem, right? So you have an ellipse that hits our plane, and then the ellipse can also be skewed itself. That's why you need two angles. So that's the one angle, and that's the second angle. and so on. And that's the date it was calculated on, and so on, and so on, and a few more others. Then comes some reserved spaces for characters. But you can see the details. But anyway, everything is here important. The exact spacing is important. This is in format. This is in fixed format in Fortran code, Fortran 77 code. So beware. So don't. So if you ever copy this into a text editor, you do not touch those spaces, and I'm very strict about it. It will fail, okay? It's very important, so do not really edit this, right? Rather take the new coordinates. You can always click on it and get the new coordinates. So just coming back to the idea of the reservation again, let's say you wanted to reserve this a month ahead, because Neowise is still going to be visible throughout August with telescopes and part of September, depending on its angle to the Earth. I would advise you, if you want to go safe, you use this. But on the day when you're going to launch your plan, go and redo this. So let's say you want to redo this. So I just say get ephemeris again. You see, that's what I'm doing. And all you do is you save over that. I'm saying create a plan for later, and you're saving over the plan. You can do that even 1 minute before your plan starts. That's fine, okay? But the reservation as such has to be at least 4 hours before, right? But that's a general recommendation for settings. Now let me jump and see if there's some questions. So I'm just going to stop sharing for a moment, and then I'm going to show you some really beautiful apps of how how you can get the nice framing. That's going to be the final part. So I'm going to just say stop sharing, and let me see if we have some more questions here. Paul, wonderful presentation. Well, thank you very much for saying that. Who funds your operation? Paul, we are a not-for-profit organization. We live off the subscriptions, really, and we dedicate all our time. Whatever there is in profit, we reinvest in enlarging the observatories. We are a bunch of crazy individuals who love astronomy just like you do, and we're trying our best to give you good service. We don't always succeed, but we are always on the stage of improvement. Okay, Paul's in Birmingham, England. Thank you for that question. Okay, Andreas is asking, without TrackOn, isn't the comet showing moved in 180 seconds? Well, Andreas, I'm going to show you that. That's a great point. It's not that much. It's a few pixels. As I said, if you want it infinitely sharp, you need an infinitely short exposure, but you get infinitely small signal, right? So it's a compromise. Again, it'll depend on the relative movement. I'll answer that in a second, because I'm going to go to a website now that is going to talk in detail, or going to show you in detail, what the relative movement really is. Thank you for reminding me. I will do that right now. Okay, I got you. Are you going to use one of your telescopes to image the comet during the session? No, I'm not. Because during this time, New Mexico skies is only going to be open in the evenings, of course. It would be nice to do it, but the second is it's quite fully reserved. And I just want to spend a moment to talk about reservation, because I got a few people saying we're quite annoyed, and I understand the annoyance. The annoyance was about, well, there are a lot of slots booked by the same people, and they've booked it weeks in advance. Now I discussed this internally, because I completely see your point. Right? So the point here is, usually every subscription, you have a certain reservation quota, right? That means you can reserve so much time, and members abide by that. That's all goes fine until you get an event like a comet. And then the experts of comets come in and say, wow, I know all about comets. I've seen this already in March, April. I'm going to reserve all the slots, and the reservation slot is very small. They are completely abiding by iTelescope rules. But here's a new problem. You get a lot of annoyance in, because you get a lot of people who say, well, I would have loved to do this and I can't. It's all fully booked. Yes, yes, and yes. So what we're going to do is we're going to change our policy, or I would say amend our policy, so that we reserve the right to cancel reservations for people who do too many. Now, this is going to cause an offense probably to some users, but it will be to the delight of the larger community, because we want to reserve that. And the second, what we also will do in future when we have such events, is iTelescope itself will reserve a window, and we will give all those images as part of your plan, right? So that you can enjoy them. You may not have taken it yourself, but it was taken with iTelescope, and that you can enjoy them. That's the suggestion at the moment, if you have additional suggestion, but that is probably a good compromise, to have a fair usage policy for everyone. So thanks for bringing this up. Do you really still use Fortran? Ha! Robert Slobins. I used to program a lot in Fortran. We don't use it anymore. No, we don't. But the scientists still do, because a lot of the codes that you have, they didn't go to Python and so on. A lot of the calculations still go in Fortran, right? And even if they don't use Fortran, the interfaces and the algorithms that they developed are so complex. And so, I mean, there's a lot of work that they would still be using Fortran, right? Okay, Jose, how does iTelescope charge time? Okay, that's another question, right? So we charge only per image. We don't charge per reservation. It's the same thing when you fly for so many minutes or hours, you charge actually the flying time and not the time you're sitting at the airport, unless you spend a lot of money in the shops, but that's your own business. Okay, so we charge only per time. You can look that up in the pricing. Andreas again, how can you enter coordinates to have the comet not in the center? Yes, Andreas, that's the second one. You're going to bring me right onto the target now. I will answer it. Jumping the gun here, can plan with comet ephemeris and centered comet retain track on if we modify it for Mosaic? Yes. Okay, Anurag, I know your question. That's going to be the final question. So he's asking, can we do mosaics with comets? Yes, you can. That's a very difficult question and very difficult to do. Not a difficult question. It's more difficult to answer or do it precisely, but I will address it. Are you allowed to print someone else's pictures? No, only if you have special permission. So the preview images, of course, you can download. That's what I'm showing also on preview images, but the answer is no. The images strictly belong to the user. They have all the copyrights. They can do whatever they want with them, right? They have all the copyright. But you can ask the person if they want to share. For example, for the next session, I'm going to work with some user images. I have explicitly asked these people for permission, and they actually got some very nice points from iTelescope in return to use their image for image processing, which will be upcoming as soon as astropixel process is ready. So that is there's a no share. It is no share by definition, and only share if you want to write to the person. Okay. However, if we as iTelescope take it, we will share it with the community. Okay, thanks. Let's get back. So let me just jump to the one question that is quite marvelous, and that is, how do we know the movement of what's actually going on? So I will do that in a moment. I'm just going to give you the link first. 1 second. Here's the link, and now let me share the screen once more, because here you go. So we are now at the minor planet center. This is a marvelous interface where all the data comes from, right? All the data that comes from. And they have this page where you can put in the comet name, which I'm going to put in now. Oh no, that's a link. So again, you have to be very precise here, /2020 F3, right? That's it. And I'm just going to go through some of the options here. This is going to give you the right ascension and declination coordinates. It can also give you the orbit coordinates lower down. So you have options here. Here's the MPC1 line that will look incredibly similar to the one that we're using. There are some minor differences, but it really is the one. So if you want the one line, you can get it here. If for some reason you don't get it on iTelescope, when would that be? Well, for new comets that are not yet in the database and are only in this database, for example, the Amaral comet, you can look up here, that's C2020-02. You could look it up here and you could get the proper ephemeris, which you can then copy into ours. In general, I don't recommend doing that. That's very far-fetched because you'll find most of the things in our database anyway. But the objective now is to answer the question here. I think it was Wilfried who asked the question. Let me just go back. Or was it Andreas? I don't remember who it was, who asked me the question about, Yeah, how much does it actually move? So we're going to answer that question. So let's go through the options here. Here's the ephemeris start date. You can put them, if you leave it blank, it's today's date. Now think about Comet Neowise for a second. When it was close to the sun, the movement, the relative movement is actually very small. So when was its relative movement maximum to us? Well, that's when it's closest to Earth and it's just passing the Earth. It's just like having a car pass in front of you. So you can actually go back in time and you can see the relative motion of that. Now, this is going to be only numerical, and later we're going to do the whole thing visual. I'm a very visual person, and I'm sure most of you are too, but I'm going to give you both options so that you're prepared. So I'm going to leave this blank here. The number of dates, now that's a strange word, dates, it's the how many columns you want printed out. The maximum that you can have, as far as I know, is 1,441 here. I got the number in there. So that's just how much you want spit out, right? So here are the details. Do you want it every day, every hour, every minute? Well, let's do hours for a moment. If you want to be very precise and you have a very close comet that really moves very fast, you can do it in minutes. I'm going to go to hours. Okay, so I got the comet name, got the hours. For daily ephemeris, don't worry about this. Here, you may enter the observatory code. This is where the observatory code, and you don't have to enter the coordinates. The observatory code, here I already got them. So for Siding Springs, I think it was Q62 for New Mexico skies. And look this up here again in the, here where are all our observatories, and you have the observatory codes here too. You can see New Mexico skies has H06. That's why I put it into the table, right? So this will automatically enter everything, right? Now comes a few other things. Leave this, don't worry about this. And now comes a very interesting part here, the total motion and direction. Now this is display motions. Now this looks, if you've never seen this, it's going to look a little bit strange. Arc seconds per minute. Well, that's exactly. So our window, let's say our window was 1 degree, right? 1 degree is 60 minutes. And a part of a minute is seconds, right? So this is how many arc seconds per minute it moves. That doesn't really give us a lot. We wanted an arc minutes per hour. So how do we do arc minutes per hour? Because your session would be typically, let's say, 30 minutes or so, or maybe even longer. So you need to know the relative movement made in arc minutes per hour. Now comes the nice thing. Arc seconds per minute is the same as arc minutes per hour. So we can leave it at that. So whether it's arc seconds per minute, for some of you will have done the math very quickly, it divides by 60 both. So the numerator and denominator cancel. So it's arc minutes per hour. Just leave it there. This is arc seconds per hour. Don't do that. That gets really confusing. So just leave it at the default. Now we have a few other options. Suppress output if sun is above location. Well, that's absolutely so because, well, unless you're a genius, invented something, I have not been able to well, and the comet is very bright, which is rarely is. I hope we see it in our lifetimes. You will not have that. So I'm suppressing output if the sun is above the horizon. Yeah. Suppress output if the object is below the horizon. Well, that makes sense, right? That's for the local. So this is all calculated for the code H06, which is New Mexico skies. So just leave it at none, and let's see what it spits out here. So here you go. You see it says, let me just expand this a little bit. So here it says suppressed. You can see this is daytime. So tonight, and this is in universal time. So again, this is unfortunately confusing. It's not in local time. By the way, everything that Telescopius shows you is in local time. It's in local time, local time, local time. So very nice. But this is scientific. It's in universal time. So you have to think a little bit back. What is the universal time code? Well, that's easy to find because if you go back on, let me just add another window here. Let me go quickly on iTelescope and show you where you get the local universal time from because it varies whether it's summer or winter. So for New Mexico skies, it is UTC -6. That's where you get it from. Is Siding Spring, but be careful. This is not a general rule. It depends whether you're in summer or winter, whether they have summer or winter time, right? So beware of that. So this is universal time 2 a.m. at the moment, 2 a.m. Go -6 from there, and that puts us at 8 p.m. That's very reasonable. So at 8 p.m. tonight, the right ascension coordinates and the declination coordinates are these exactly on the hour. If you want it more precise for whatever reason, it's not necessary to do it anymore. And you can do that. But ignore all this. This here is an important one. What is the sky motion in arc seconds per minute? Or as I said, in arc minutes per hour. This is moving 4 minutes, arc minutes per hour. If your window is 1 degree, it's moving 4/60. So that's maybe about 7%, 8% in your window. That's how you get that detail. And you can put it in arc seconds per window, per minute for those who want the detail. So that's quite important. Now you will see on the 23rd of July, if you went back, I won't do that. Now I'll leave you that as a home exercise. You will see this goes all the way to 9 or 10. It's quite a lot larger. The relative movement is a lot larger, right? So that varies. So 4 is quite typical, and it goes further and further away. This will go lower than 1. Also important here is the altitude. The altitude, how high is it above the horizon? That's really important. So it starts off at 8 p.m. at plus 48, but it's not quite dark there yet. Goes to 36 and so on. And then you can see it's suppressed here after 5 a.m. 2, 3, 4, 5, 8. So that's at just before midnight. And it completely disappears, but it disappears, you know, that is when it goes below the horizon. Unfortunately, they don't have the option to give a 20-degree line, because the 20-degree line would be at least 1.5 hours before that, right? But that's how you read these coordinates. Very useful, by the way. So do use this website. And that also gives you, and that's the next step, gives you the right ascension and declination coordinates. So I'm just going to copy this for a second, just like that. Copy function. And then you can jump in here. And if I go to the third option now that I want to show you, go to the deep sky menu. Again, you're going to call it, I'm going to call it neowise, and I'm going to call this right ascension and declination. That's how I'm going to call my plan, so that I can remember this, because now I'm putting the static coordinates in. And the target name, now, if you put in neowise, it's not going to recognize anything. It's going to go get coordinates. Object not found. Well, it's not in the database, right? Because you're not using the ephemeris, right? It's not a fixed thing that we have. So you just give it any name. I'm just going to call it neowise RADAC at the moment. Now I'm going to paste in the right ascension and declination. So I'm just going to delete. Now this is just my way of doing it. I'm going to delete the right ascension, the declination part. You see that? You should actually do it separately. I'm a little bit lazy. I'm just going to, hang on, I deleted a little bit too much. Let's just put this in again. So you can see here's there's the first part and there's the second part, right? So you obviously need to delete the second part, or you just do Control X, you just take it out. So that's the one part, and then I'm going to put in the second part here. That's the declination. I'm just being a little bit lazy. We can ignore the plus sign. And then that's all you need. You do your plan. I'm just going to do that very quickly, just as an example again. 1 luminance, I'm going to do it 120 seconds, okay? Leave it on binning 1, and you can do the rest too here. Let's just do it for clarity's sake. So I'm going to go again to red, 60. In this case, you can do 120 to 180, but we are often pressed for time. Sorry, it's the wrong way. Make this 3, and this one, I did it exactly the wrong way. 3 luminance, we want the sharpness through the luminance, and 1 through each of the other ones. There's red, green, and blue will follow. And don't forget to fill these all out. And don't forget, in this case, I'm going to binning 2 to get a quick signal and put 1 here and make the blue. And that's going to be your plan in general. So there's your color. So very similar to the other one. And that should give a fine image. But again, that's going to put the head in the center. That's not really what we want. I just wanted to show you how to put in coordinates, because once you know how to shift coordinates, then I've answered the final question. So let's just say create a plan for later, which I'm doing. So that is now a saved plan for later. That'll be true for 8 p.m. that evening. Again, if you want to reserve in the future, do a dummy thing, do a dummy plan, use this plan, and just save it. And the day your reservation comes, go and look the proper ARI and deck coordinates up and overwrite the plan. Same trick again, right? So that's it. So now we get to the exciting part. So we've done all this, but now how do we really frame the picture? And that's the final part I want to concentrate on now. And I hope I'm not taking too much of your time, but it's quite an exciting. You've got so many good questions. So I'm just going to stop sharing and just make sure I answer all your questions. So we are. Let me see. Where are we now? Yeah, here. Can we take infrared pictures? No, again. So the question is, how do you define infrared? Okay, infrared is a very long, broad term from an optical perspective. Our eyes typically see until the dark red. We call that the very far red, right? So from there on, we can't see anything. CCD cameras can see a lot more. They can see from 700 to about 900 or 1,000 nanometers, right? That's much more in the red. We call this, we would call that the far red or the very near infrared, right? The very near infrared, right? There's one camera that can do this, and it's on T17. It looks all the way to 1,100 nanometers. So there is a possibility to if you take the clear filter, you get the whole spectrum. So you can actually, that way you can look very deep into nebula and you can get that type of detail. But that's as far as you can look with CCD cameras. If you go beyond that, you need cooled liquid nitrogen cooled cameras, which get really ugly, right? And then you also have the water vapor from the atmosphere that are going to give you absorption lines in the picture, which are also not very nice. So I hope that answers your question to about 1,100 nanometers with T17. However, T17 is a scientific camera, right? It's a scientific camera. It's not giving pretty images. It's meant for deep space, and it has a resolution of 1 megapixel, which is not really pretty. But if you want such details or go deep into a nebula, you can use that for that. Okay, I hope that answers your question. Robert, again, yes, can there be an image library? It really doesn't matter who takes the images. The key is the processing. Unless someone has a particular agenda, I could just download the data and process. Yeah, well, you know, Robert, that's a great thing. So what we're going to do at iTelescope is we're going to create such an image library for you. So from come next month, we're going to start giving this to some plans. I think it's going to go from plan 40 onwards, where you're going to get these images every month, very good images, and you can process them. Okay, so the answer is yes, we're going to do that. We're going to do that. The other thing, if you want to share images with other people, you're very willing to do that. Go to our community, community.iTelescope.Net. Most of you will have the link, and you can happily share images also among yourselves. If that is what you like to do, just put up a message on the forum, and that is another way of doing it. Okay, so so I think we've answered all these questions. I haven't clicked. Oh, we had so many questions I haven't answered. I've answered all these questions. So I'm just going to say done there. Well, I'm not going to go through done everything, but yes, I think I've answered all your questions there. So let's jump to the exciting part that I really wanted to show you is the visualization of the comet. Okay, that is, how do we really model this correctly? And I'm going to jump here directly onto, let me just see, where's the screen? I'm going to jump onto my iPad, right? I'm going to jump onto my iPad now. I'm going to share my screen again. Okay, so you should now be able to see my iPad. And you know what's so interesting is we used to have software like Stellarium, but Stellarium is completely outdated now. I mean, it's free, but honestly, it sucks. And I don't mean that in an arrogant way. It really doesn't work anymore because the apps have completely overtaken. I was initially going to show you Stellarium, but I decided to change my mind because I went so deeply looking and researching apps, which are good apps to use for comets, and I found something. And it's really quite inspiring, but these are apps, right? So that's why I have my iPad connected. So you can see here, I'm going to click here on, and I'm using this on a remote screen here. So I'm clicking here on Sky Safari Pro. I'm not a seller of Sky Safari Pro or anything. It's just one where I found, and I think there are a few other ones that do a similar good job. But I'm going to give you one example that really does it beautifully, right? So this jumps into Sky Safari here. And it does a very nice, so when you, you know, the simulation, so I have to do this on my iPad now, not on the real screen, but you can see I can shift here, this is a virtual picture. I put ourselves, if you look at the arrow on top here, in New Mexico skies, so that's where you need the coordinates. So I've put all the locations of our telescopes. I put this especially for New Mexico skies because that's what's coming up tonight, right? And of course it's daytime right now, and you can rotate it around, and you can see there is the horizon map. That's the horizon coordinates. That's 0 degrees on the floor, and then it goes plus 30 degrees, so you can see the 30-degree line here, and so on, right? So I'm standing here looking at the sky in real time at the moment in New Mexico skies, which is 12:28, so that's 1 hour ahead of me. So this is in local time, very nicely done by the software. It always, as soon as you put in some local parameters, it does link to the real local time, taking daylight saving times into account, which is quite important. That's the coordinates again. So what happens tonight, right? So as you can see here, I've got the time scale. You've got some settings which you can customize. But let's jump ahead. So it's jumping at the moment at 1 month. I don't want to do that. I'm just going to do, and I'm going to go in 1 hour interval, right? So I'm just going on 1 hour. So let's go back on now, and I'm going to go 1 hour ahead. So this is going, following the side. I'm just going to go until it gets really nice and dark. Here about, that's nice. So on clear skies, and in the simulation world, this is always clear skies, which is a wonderful thing to dream about. This is what it looks like, right? That's south, and there you look towards north and northwest, and this is usually where the comets are. So where is that comet then? So in this case, it has a very nice function. I'm going to find the comet. I'm just going to go here to the search window. You can see it here on the bottom left. Just put the arrow here. See there where it says search? I'm going to click on it now, and there gives some, so it says, gives you all kinds of different objects. I'm going to click here on brightest comets. You see that here, brightest comets? I can't click on it because it's an app, obviously, but I'm clicking here with my finger, brightest comets, and there is Neowise. I'm going to click on it. So here it gives you incredible details, and all you have to do is go down here. See, I'm pointing the arrow here, and you click on it, and it says then here, center. So I'm going to center on it. And there you go. It's now centered on Neowise, right? So I'm going to expand the window, and beautifully the tail is correct here. I checked this on a lot of your members' images. I went to painstakingly, I went back to the dates and I checked everything, and it really matches. What's interesting is the length of the tail. Now the length of the tail is a simulation, but it's quite accurate actually. It's quite accurate because the length of the tail, if you go back in time, I won't do that now, but you can really see how it gets longer and shorter. Quite beautifully done. It doesn't have the iron tail, but anyway, it does, it does give you the correct orientation of the tail, which is good, which is great, okay? And I'll get to it in a moment. Remind me if I forget, but I want to show you what Telescope is going to be up to in this next stage. Quite exciting. So here we are, and that is exactly what it's doing at the moment. You can see there's some window, and what frame are we looking at right now, right? What's the frame that we're looking at right now? And before I talk about the comet position, I'm just going to tell you what this field of view is and why it's good to do. I'm going back to the observe button. You see that where it says observe? I'm pressing it now, clicking, and I'm going to click here on scope display. Click on scope display. And in the scope display, I have custom field of views. Now, unfortunately, you cannot name those custom field of views. In fact, I wrote a long suggestion yesterday to the authors here to suggest that it would be good if this was customizable, if we could customize the field of view here with a name. So I would say this is T14 and so on. So you can see at the moment here, I have enabled a custom field of view, which is 3 degrees by 2 degrees. Let me just click on this with my finger to show you how this is done. So you need to enter 3 by 2 degrees. By default, here, it is always in a circle. So it's just it's just like you're looking through a viewfinder. But you can change that here to the area here, the rectangular area, and that enabled me to do a 3 by 2 degrees. Where did I get the 3 by 2 degrees from? I went to the telescope overview, and I just looked at the field of view. Now there's one additional important thing. The orientation, remember that, the orientation. So we can do that. I can scroll down now. Sorry, let's just say done. No, I have to get back into it. Sorry about this. Let me just get back into the scope. Here we are. So this is enabled. So you can see there's a field rotation angle. See that field rotation angle? That's what we can change. And that's what I meant about why the orientation is important for your selection, why we need to know that for each telescope. There's one thing I would just like to make sure that you know this. It's important in the app. This is disabled by default, so that if you do get the app, make sure you enable show even not connected to telescope. If you don't have that, you'll be wondering, where's that window? And you don't need to enable the telescope mode because you don't want to configure everything, every single telescope. It's an absolute nightmare. You just need the field of view. So that's why. So remember, enable show even if not connected to telescope, specifically for this app, right? So here comes the field rotation angle. So I'm going to click on it now, right? So I'm going to click on it in my app actually. And you can now change the field rotation. So by default, it's, now this may be a bit confusing to you. This is north and this is east and west. And it looks a bit confusing because we are in the horizontal observer mode. We are not in the equatorial mode. So let me just jump from the horizon to the equatorial mode so that you can see the orientation will always be facing upwards, right? So it's again a different view. If you stand there with your camera on the floor, you'll be standing like that. If you have the telescope's view, you are pointing north and it will be actually pointing upwards then. Maybe a bit confusing, I understand, but I just want to change that. So I'm going to go into the equatorial mode. I'm going to show you how to do that. I started off in the horizon mode because I wanted to show you the, the virtual ground and the elevation and all these things that are quite important, right? But this app doesn't have the possibilities to show both at the same time. So I'm going to show you how to do it. It's really quite simple. You see where it says settings here below? I'm jumping on settings. And you go, we are now in the coordinates. You see where it says horizon here? I'm just jumping from horizon view to equatorial view. And I just press done. Okay, and now suddenly the picture looks completely different, as you can see. This is exactly how the telescope sees it. North pointing upwards or downwards doesn't really matter because it's symmetrical, right? But that's the orientation you always see. That's your horizontal view on your telescope that we have. And now let's go back and configure this correctly for T20, because remember I said it hasn't got the landscape view, it's got the portrait view. So we can do that. So you need to now go back to observe. It gets a bit confusing, right? You don't do that in settings, you do that in observe. I'm going to press that now. I'm going to press scope display again. And here we are again. I got my custom field of view. Remember again what I told you, show even if not connected. And now we're going to go to the field rotation angle, right? I'm going to press that on with my finger here. And here's our field rotation. You see it has an angle 0. And here, oh, I'm always tempted to do this with my mouse. But of course, now I'm doing this here with my hand. You can change the field rotation. So you just change it to exactly what you see. I think it was somewhere around 91 degrees. So that's your correct orientation. Now, doesn't this look very similar to what we saw before, right? So now this would be the ephemeris view that you would have of the comet, or it would be the view that you would have if you chose the right ascension declination of the core, right? So let's just say done. So I'm just pointing my mouse there, pressing with my finger, I'm pressing done. So that's what we have. And now up here are the right ascension and the declination coordinates of our comet, which we've centered on. I'm just going to press center again. This is centered and locked to it at the moment. So if I change the time, it'll always be centered. It's moving along with the comet. Well, that's not what we really want. We want it to be unlocked from that. How do I do this? I'm just going with my finger and I'm moving this around. Look, now I'm moving this around in the sky and it moves with the sky. So what do you see the coordinates, how they're changing up there? Look at the right ascension declination. It's changing. So now I can start framing it beautifully. Now, unfortunately, the portrait mode is not ideal for this situation of the comet, but we can't change that all the time, but you might find a telescope where it is actually possible. But anyway, you can frame it now, and you can get at any time. So this would be at 2129. You can see that's the right ascension and declination. They don't have a copy function, but this is what you copy. Don't copy the degrees and don't copy the hour, just copy the 13.45, whatever. And again, I did that in the settings. I didn't set them as hours, minutes, degrees, but I set it as a decimals. If you can also copy the hours, minutes, and degrees, it'll accept it. But I, in general, like to work in decimals because then I know what I'm doing and I don't, by mistake, take in some characters that may interfere with what I'm doing. So there you are. Here you can frame it. And that's your real, that is the center of the frame that I'm seeing. So the center is just divided into 4 now. This is not a mosaic. That's the next stage I'm going to get to. So there you are. You have your central coordinates, and that's an easy way how to do it. Now let's just, for fun, see how much is that comet really moving visually, what we saw before in arc seconds per minute or in arc minutes per hour. So let's change this by 1 hour and let's see the relative movement in our frame. What would happen, right? So I'm changing this. I'm going 1 hour ahead and another hour ahead. And you see how it's moving in our frame now. It's quite incredible. You see how it moved from the middle. So you can actually estimate the real-time movement here. And it's quite beautiful. We're going back to now again. So I'm moving this back again. And again, I can move forwards or backwards in time. And you get a very, oh, this is in seconds now. Sorry, wait a second. I don't know what happened there. I meant hours. Go back to 1 hour. Go back here. Okay, there we go. Don't press the very left button or the very right button. It just does a very fast animation. So be careful with your fingers. I got big fingers, so I often press the wrong button here. But there you go. Now you can really study in detail. And I think that's the most visual way of doing it, what this movement of arc seconds per minute, of arc minutes per hour actually really move. And I think that's not bad. That's not bad. So I'm just going to stop for a moment and just unshare this and see if there are any questions before I go to the final. I know we've been going on for a long time, but I hope this is also some useful and enjoyable information for you. So let me just see if there are any questions here. Okay. Robert was the last one. Okay, no other questions. So that seems to be crystal clear. Well, that's great. I'm going to go back to the share screen now and share again with you. There we go. So again, this is how you do it. So again, you can fix it by going on the center. If I do center, it'll fix your line. It'll go right back and center your object again. Give the coordinates as you would find them resolved on iTelescope with the different methods I've just mentioned. And then you can move it around in the window. And this is really important if you have more distant comets, right? And you want to, sometimes you can use the software now or other stellarium planetarium softwares. You can use them to frame your pictures ahead of time. You can go through comets and you can say, oh, that came close to a star cluster, or that came close to a nebula or some other, or to a galaxy or whatever it may be. And you can frame your picture that way, right? So it's quite useful. Right, so the final part that I would like to do now is going back here and just answering the question on mosaics. Creating a mosaic, yeah. So I have added this now because mosaics are a little bit complicated. So I'm just going to refer to the link here quickly. I'm just going to give you the link. I'm not going to spend too much time, but can you do a comet mosaic? And then I'm going to show you what Telescopius is up to, right? That's the final thing. So I'm just going to say stop share for a moment. Find my window again where I can share this with you. There we go. And I'm going to share my screen back again. Okay, so this gives you a bit of indication, explanation how you can do mosaic, right? But the good news is, don't worry too much about it because Sebastian is working on an amazing solution here for Telescopius. So what are mosaics? I'm just going to quickly go back into the view just to show you very quickly. I don't want to spend too much time on this. But if you go here to the Deep Sky menu, and I'm just going to press on any object here now, if you want a mosaic of this object, See, here you have a very small field of view. That's a great example. You copy this for iTelescope, you copy all the coordinates, and then you can paste them in. I'm not going to go into the details now, but you go right back here to creating a mosaic, and you paste it into this window here. Into the lower window that gives you the coordinates. Just read this in peace. So you could even frame this with a comet. You could do this. It's a little bit more complicated. So for a comet, if you wanted to do that, what you would do is you would have to go back to the app. 1 second. You go back to the app, and you would have to know what the central coordinates are. I'm going to go back, center it. That's not doing it at the moment. Wait a second. Oh yeah, of course not, because I'm here. So here we are. You center it, you remember those coordinates, you go over to the mosaic, and you create your mosaic pattern from there. That's just a very short answer. I don't want to go into too much detail, but you can create a mosaic. Now, finally, what I'm going to show you is what Sebastian's up to, because I've asked, we corresponded a lot with him on Telescopius and said, how can you really improve things? So this is what he sent me last night, what he's working on. So as ambitious as he is, he's working on even more. So this is his vision of stage 1 of introducing comets to Telescopius. So what he's going to do is, so you can see here is the window for the comet, right? And you will be able to get the dust tail and the iron tail from the website that I've showed you earlier. And then it'll even show the iron tail. So he's very ambitious in this. I don't know how realistic all this is. I hope it is. But what would be, of course, very nice if one day we would have the comet in real time with the iTelescope window with all the options that you could think of, right? You have the tail, and you can really frame it beautifully, and then you just copy and paste, or it's even transferred automatically to iTelescope in a further version that we have to work on. But that's where that's where the vision is, that's where we're going. And I think then you're going to have an incredibly beautiful tool. Well, anyway, on that note, I'm going to stop sharing now and say thank you very much to all of you. Can we get the DSLs to appear in this view? Yes, Robert, that was my answer to that, right? So that is where it's going. Do you have any plans to field rotator? The answer, Eric, is no. I'll tell you why. Anything that is mechanical, and you know from mechanical engineers, will break. We had a field rotator on a telescope called T27. The problem with field rotators is they are very advanced. They're very advanced, and they cause a lot of misery for most people. So we'd rather introduce more telescopes with, like someone just suggested, why don't you have a wide field? Why don't you have that? So rather increase the number of telescopes, but we want to fix it because mechanical things, there's no fast field rotator. Believe me, we've gone through it. For the applications for iTelescopes, we put strains on equipment like nobody else does, really, because you use them all night in any situation. And that's really the reason why we don't want to introduce field rotators. They will break down. They do break down. And if you go with a field rotator and you look right at the zenith, this thing is rotating like crazy. So that's the reason why it's really for the advanced users. If you want to do something with field rotators, you insist on it, then go to the hosting or try and host with a few people, okay? Anyway, I hope that was informative, and thank you very much for your time. It's been incredibly long. Thank you, John, James, Rex, Robert, and all the kind comments coming in now. And thank you for being with iTelescope, for the time you spend. We do really appreciate, and we very much appreciate, you know, the time and effort you put into it. We are always on a track of improvement. We're not perfect, but we're really trying something better. So thank you for everyone. And if you're interested, by the way, and you can really write the comments very quickly, I can give a special whilst we're waiting for the for Telescopius and also for AstroPixel process to get ready with better Comet algorithms. I could give you something on time-lapse. Let me just show you the time-lapse again. in the background. If you're interested of how to do a time lapse with a DSLR, I can do a special one on that. If you would like that, say yes. And I can make my images available to the public, which I will happily do, so will be able to download them. And I can give you a special how to get a time lapse like I did there. You know, what is behind that? Yes, 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 I see it. Okay, that's nice. So I will do that. I'll prepare that in about 3 weeks or 4 weeks. Will be fine. If you like time lapse, again, that is really for the specialists of you who like to do outside stuff. I'll give a free one on time lapse. Okay, so that's very nice. And anyway, thank you for all your time, and thank you also to my friend Mark Horner, who was sitting in the background in case my thing would collapse. It didn't. So thanks Mark for being here and jumping in just in case. So fortunately, my computer didn't break down. Thanks. Have a wonderful weekend wherever you are, and thanks again for being with iTelescope. And I will send out the recording in about a day. I'll work on it, and then you will get it through a follow-up email. Thank you very much. Thanks.